And we're back. So this is example 3, and we are still in sections, let's see, 2.1 to 2.2, and we are looking at normal strain. Okay, and so remember normal strain, normal means perpendicular, so we're applying that load, okay, and we are increasing in length, and, whoops, you can't see into that, we are increasing in length. And normal strain is change in length over original length. And it's positive if we're in tension, getting longer. It's negative if we are getting shorter. So we have a force applied at the handle of the rigid lever. That's important that it uses that word so that we know it has rigid body rotation, because we are in rigid body mechanics. So we have rigid body, okay, rotation. We're not going to have any bending or deformation of that bar. It causes the lever to rotate clockwise, so clockwise, about the pin at B through an angle of 2 degrees. Determine the average normal strain in each wire. The wires are unstretched when the lever is in the horizontal position. Okay, there's 2 important things here. Okay, well, probably more than that, but it's a rigid body rotation. So the other thing is, for some reason, in statics, you all are great about drawing free body diagrams and including forces at pins, but something happens to your brains when you come into strengths, and all of a sudden, it's like you don't want to include any of these forces at B, and so we get all sorts of weird things going on. But what we have to understand is, if we were to actually be drawing a free body diagram in terms of I need to find forces, okay, here's that force P that's coming down, I would have these forces in these cables, okay? And this is a really, really important concept to remember, because when we get to the next chapter, we're going to start finding these forces in the cable, because we'll understand maybe what material it is. So we'll have a stress-strain relationship. And this would be an indeterminate system, because I would have 1, 2, 3, 4 unknowns, but for some reason we get in here and all of a sudden it's floating in air. So always remember, if there's a pinned pin, you must include it. On this one, we aren't really finding reactions. We're just trying to find the average normal strain. And so if I see normal strain, I know that normal strain is change in length over length original, which is length final minus length initial over length initial. So that's all we're doing in this problem. So I'm going to just go ahead and draw it on my system here. And we are going to over-exaggerate this because it just makes it easier to see. So here's that rotation. And so when I look at this, this hand is going to come down some amount. This is going to stretch some amount, so we're going to have a change in length from D to F. We're going to have a change in length of this cable, and we're going to have a change in length of this cable. So I've now marked all of those. We could also have a change in length of, or direction of where our hand is. I guess that says E, okay? So I could say, well, how far is the hand pulling it down? And when you look at this, what you can see now is we have this great little, okay, we have this great little set of triangles, and we are going to use, in this class, we are going to use a whole lot of similar triangles, because that's what the rigid body rotation allows us to do. So I have delta H, okay, I have delta CG, I have delta DF, and if I had actually drawn this correctly, we could have also shown delta of the hand, okay, and we're rotating about that pin. I know that this is 0.2 meters, this is 0.3 meters, 0.2 meters, it doesn't give us this length. I know my original length of CG equals the original length of DF equals 0.3 meters. And I know the original length of AH equals 0.2 meters. Okay, so I have everything. And I'm told that this is a 2-degree rotation. So what do I need to do here? How can I figure out these deltas so that I can go back and figure out strain? Okay, so let's just look over here. I know this is 2 degrees. It's rigid body rotation. So I have 2 degrees, SOHCAHTOA, right? SOHCAHTOA. 0.2 meters, and we have 2 degrees, and I need to find this value right here. So is that sine, cosine, or tangent? What am I using if I know my x component and I want to know my y component? Okay, that's going to be tangent. So tangent of 2 degrees equals TOA, opposite, the change in length of AH over 0.2 meters. And when I work this out, I get that delta AH equals 0.006984 meters. Okay, so now the strain in AH equals delta AH divided by the length original of AH. 0.006984 meters divided by the original 0.2 meters. And I get that the strain of AH equals 0.035 inch per inch. Okay? So now I can work on, work on wire CG. So if I'm looking at CG, it's the same deal. I have 2 degrees. I have a 0.3 meter in the X. I need to find that Y. So tangent of 2 degrees equals delta CG, okay, divided by 0.3 meters, opposite over adjacent, and I get that delta CG equals 0.0104762 meters. So now I can find that strain of CG. It's 0.0104762 meters divided by 0.3 meters, and I get that the strain of CG is 0.0349 meters per meter. I don't know where I came up with inch per inch there. It doesn't matter. It's unitless, so whether I'm looking at an inch per inch or meter per meter, but in this case, you know, meter per meter. Okay? So now that I have delta CG, I don't need to do tangent again. I could do tangent again. I could say that tan of 2 degrees equals, but now I'm looking at 0.5, okay, delta DF over 0.3 plus 0.2, because remember I have to look at this whole triangle, or I could use similar triangles as well. And I could say that delta CG is to 0.3 meters as delta DF is to 0.5 meters. And you have to go back and look at the entire triangle. So if this right here is my first triangle, then when I go back, I have to make sure that I include that whole length because we're coming along that same slope. And again, this is a common mistake. Students will take 0.3 meters and then just call the next distance 0.2, but you have to remember it's coming that same slope, so you have to come from the same starting point. So if I do this, well, I found delta CG right there, and using similar triangles, I can find that delta DF equals 0.0174638 meters. Okay, so the strain of DF is just 0.0174638 meters divided by initial length 0.3 meters, and I get that strain of DF is 0.0582 meters per meter. Okay, why are these two the same? Okay, why are these two the same? This is 0.3 meters over, this is 0.2 meters over. Why are these two the same? Do you see the ratio of their lengths? Okay, this is 0.3 meters, this is 0.2 meters. So the ratio ends up being the same amount of stretch, if you will. And this one should be longer. Okay, DF should be longer. We can see that it is. And if I wanted to calculate the hand and I knew the rest of this length, I could. But this is where you all, please always say to yourself, does this make sense? If you made the mistake of just calling this 0.2, okay, 0.2, you're going to get a different answer here. you're going to get a different answer. And you should be able to say, oh, that's not the way it ought to be. It ought to be, this number ought to be bigger.